If we had started with the exponential Fourier series and then taken the limit like we did with the trigonometric one, we would have derived the complex Fourier integral directly. But since we already derived it for the trigonometric Fourier integral by taking a limit of the trigonometric Fourier series, we'll start with the trigonometric Fourier integral. And if you put it together, you know, we had formulas for the Fourier integral. In general, it was up here. Oops, how did that happen? There we go. Sorry about that. Well, here's the complete Fourier integral, the trigonometric form. If we put it all together, where we put these formulas for big A and big B up into here, we get this top line here. And then we manipulate that a little bit. I think we use a trigonometric identity here. This mess can be simplified. This mess is just cosine alpha quantity t minus x. If you keep going and using Euler's formula, just keep manipulating this, you'll end up with this. It says this f of x equals this thing in terms of exponentials instead of cosine and sine by using Euler's formula. And the coefficients in here, here's the formula for those. So we have an exponential version or the complex version of the Fourier integral. Like I said, we could have derived that directly from the exponential Fourier series and taken the limit. But here we use the trigonometric Fourier integral and then use Euler's formula. So anyway, here, the new version of the complex of the Fourier integral. So let's do this example. Say here's our f of x. In this case, it's neither even nor odd. But first, we'll find its trigonometric Fourier integral. Our a, by using the formulas, since it's only non-zero for positive x, we integrate from 0 up to infinity. The function is e to the minus x. We have to evaluate this integral. There's different ways to evaluate that integral. I use what I call the Laplace trick, because this looks just like the Laplace transform. I change the x to t, make s equal to 1 in the Laplace transform. This is the Laplace transform I'm evaluating. Cosine of alpha t and evaluating at s equals 1. Look that up in the table. There's the Laplace transform. Evaluate at s equals 1. You get this. There's other ways to do that. B, this is the formula for the big B's. And it just will evaluate, this integral will evaluate to that. I don't want to spend too much time just evaluating an integral. So here's the formula for the Fourier integral. And if you look at it, I could put it, well, it is all under one thing. I could simplify a little bit. Here is the Fourier integral for that function using the trigonometric Fourier integral. Now let's do the same thing using the exponential Fourier integral. Same function. The good news is the coefficients. Here's what the coefficient is. The formula we just had here. This guy. Here's our function. Put it into the formula. I'm multiplying e's. I just add their exponents, and I don't need a table or any tricky. the integral is easy to take in this case. E to the ax type thing. Evaluate it between the limits, and I get this. We don't like complex terms in our denominators. We get rid of them by multiplying numerator and denominator by the complex conjugate of denominator. Here I just switch the signs, but here's where I'll do that. So I'm multiplying by the complex conjugate top and bottom, and here's what I end up with. So we put that in our formula for the Fourier integral. Here then is the answer, but we're not satisfied with it because we've got this complex term here. We're taking a Fourier integral of a real function. We should be getting a real answer. This has not real. It's got a complex terms in it. So Euler's formula to the rescue. We'll convert this using Euler's formula, which says it's that e to the minus I alpha x is this thing in terms of cosine and sine. And now here we're going to break it up. We'll distribute this 1 plus I alpha. Here's all the terms. Here's where we got to look at even and odd stuff. You could do the lazy man's thing and say, I'm just going to get rid of everything that's imaginary. But let's make sure we're doing it right. Let's look at what's even and what's odd. With respect to what? With respect to whatever your variable of integration is. It's alpha. So let's see. This is an alpha to the 0 power. This is alpha to the 2 power. Those are even powers. Sum of two things that are even is also even. Cosine is even. Sine is odd. Cosine is even, but alpha to the 1 is odd. Odd times an even is an odd. Here's an odd times an odd, that's even. So when we multiply them together, even and even is still even. So we'll keep that part. Evens and odds become odds. When I integrate them over a symmetric interval, they integrate to 0. So all these even times odds become zeros. I'm only left with the evens times evens, which are still evens. Here's what it is put all together, and now it's in all real terms. And since this whole thing is even, instead of integrating from minus infinity to infinity, I can integrate it from 0 to infinity as long as I multiply by 2. So here's the simpler version of Fourier integral of this guy. And we did it using the exponential term, and it should look like the same thing we got using the trigonometric Fourier integral. So quickly now, this was our Fourier integral. Here was the formula for the coefficient in here. Now we're just going to redefine things. We're going to call this thing the Fourier transform. And we're going to call this thing, well, it is the exponential Fourier integral. It's going to be the inverse Fourier transform. Here's the Fourier transform, which is this. Now we're going to start using big F, little f for the x function, big F for the alpha function. And the inverse Fourier transform is this guy, otherwise known as the exponential Fourier integral. But now we're going to call it the inverse Fourier transform. So we now have a Fourier transform pair. Now here's where things can get confusing. Not every textbook finds these things the same way. Some of them use opposite sign conventions. They'll have a minus I up here and a plus I here. I think it's a difference between mathematicians and physicists versus engineers. And even though this is engineering math, I believe this is the way mathematicians and physicists do it, or at least mathematicians. But we'll stick with the way mathematicians do it in this course, even though it's engineering math. So anyway, there is our Fourier transform. And we're also going to have sine and cosine transforms. And I'll just say, here's what they are. I'm not going to derive them. I'm just going to say what they are. And they have their inverse transforms. Here they all are. Get into using them in future